why we need to go for the mechanical testing. Okay, so here is just a few schematics where in practical scale where we can show you that why we need to do the testing of a material. Okay, so can you see the figures that I have attached here? So
yes, sir.
Yes,
so
sir.
can you please tell me that what is this particular picture tells us? What is this picture? Hello?
Airplane engine.
Yeah, airplane engine and and what is this? This is a blade, right? Now, generally, you will
Yes,
find
sir.
that during service life for a long time, so these blades may break. Okay. Now, what is the main cause of breaking this particular, blade that generally rotates at several at different environment condition? Sorry.
Sir, fatigue, sir.
Fatigue and creep, sir.
That is partly answered. Okay, so can you please
Creep and
add more things?
creep, sir. Creep.
Yeah, sorry. Can
Creep.
creep? Okay. Now those who said fatigue. So what is the reason of saying the fatigue? You said correctly, huh? Why you have said it is fatigue failure? Or generally fatigue failure happens?
It is subjected to fluctuating loads. Sometimes that may be the reason for fatigue.
Yeah, the fluctuating load. Okay, now the fluctuating load means the loading start from what to what level? Means the maximum level you probably don't know, but what is the minimum value of that particular load? Maybe zero. When it is in a rest condition, that may be zero. Okay, if we neglect the load or the weight of this particular blade, okay, and when it rotates at a maximum speed, so that the maximum load can experience. Now, someone said the creep. So why creep?
It is subjected to high temperature.
It is subjected to high temperature, and of course, during rotating, some load is experienced by this blade. So, at high temperature, loading conditions is there, right? So
Yes.
that is why we can say that certain cases the failure that generally happens may be due to fatigue as well as the creep. So I think from this figure you can say that not a particular the loading condition is not responsible for failure of a parts or of a components. Rather, it is a combination of the different loading conditions, right? Now we will talk about later that what is the material that we generally used here, and what are the parameters that actually control the failure of this particular material. We will talk about subsequently. Okay, but coming to the next picture, what is this picture? I think civil engineers will know these pictures very well.
Suspension.
Bridge. So what kind of loads that bridge can experience?
Say dead load, live load, wind load, seismic load.
Sorry. Can you please say quite loud?
I said dead load, live load, wind load, seismic load.
Okay. Now, in a rough scale, which we generally know as in mechanical testing courses, that certain cases here I have shown you that what is this kind of load? Compressive load. And certain places you will find that the tensile load is also available, right?
Yes, sir.
Now, what happened at the center of this particular bridge? If bending load, okay. So here you can see that this, yes, experience a bending moment or bending load. Okay. Now, in order to test the material which are used in the construction, Considering the load that the bridge can experience, we need to test the material before using in constructing the bridge, right? So I think you have roughly know about you have roughly said about the mechanical tests we need to go for constructing the bridge. So what are those tests that we need to go for based on the load? In this particular figure, you have said the fatigue and creep. Okay, and in order to increase the fatigue and creep resistance of a material, we need to do the test of fatigue test and the creep test, right? So here, what are the tests we need to do in order to increase the life of a bridge, or in order to increase the performance of a bridge?
The compression test and bending test.
Compression test, bending test. Okay, and another things?
Impact load.
Yeah, impact load, you can say when some heavy truck collided the pillar of this particular bridge. Okay, so in that cases you can say the impact load is required. And the most common part you have missed.
Sir, the endurance test.
Sorry?
Endurance test.
Endurance test, yeah, partly you can say. What about tensile test? So here you can say that the long wire, which we basically use in the constructions of bridge, okay, suspension wire, okay. So for that particular cases, you need to go for the tensile test. I think तुम्हारा विवेकानंद से तो देखे जो long wire जिगले use है ना. So those wire basically used before using the engineers did the tensile test and the certificates. Actually, the tensile test result they have verified. The engineers have verified before doing or before applying for the constructions of bridge, right?
So wind tunnel test.
Wind tunnel test, wind tunnel test. Here partly used, okay, but here we do not talk about the wind tunnel test, okay. There's some specific or the basic mechanical testing things we will cover in this particular course, okay. And another things, just like the previous figure 1 where the temperature was a sensitive part, so here also you can add the effect of temperatures as well as wind on the variations of the mechanical properties, okay. So how they affect on the performance of the material. So so sidewise you can say that we need to study that part also, okay. And partly I should say that when we do when we study the impact test, so there I think we will talk about the effect of temperatures on the impact energy absorption capacity. So there I think I will talk about, as well as when we talk about the tension test. So there also the effect of temperature on strength property. So we will discuss about that. Now here the third pictures where a certain failure.
একজন ওয়েট করছে স্যার, মানে আপনি কি এন্ট্রি দেবেন?
Okay, I'm sorry. Yeah. Okay, now the third figure. Can you please tell us that what is the reasons for the failure of this particular chain?
It's a tensile failure.
Tensile failure. What about the fourth one here? The rail track.
Compression. I have a shock load, impact load.
Many things can happen here, huh? Shock loading hote pare, compression hote pare. If you consider the time, bending can happen. Any other things can happen?
Sir, here fatigue also can be one reason.
Fatigue also can happen. Okay, now if we consider the long period of time from summer to winter, then can you
Sir,
think of
thermal expansion?
thermal expansion and compression? Okay, sorry.
Or temperature stress.
Sorry.
Temperature stress, sir.
Yeah, those are the influencing factors, right? So we'll talk about that. I think how they will affect on the deformation as well as the fracture mechanism. So I will talk about a little bit later. Okay. Now, what is this picture tells us? What is this thing?
The gear failure.
Gear tooth failure.
Gear tooth failure. So why this failure happens?
Sir,
Bending failure.
this one also due to impact shock loads. Bending failure.
Yeah, impact short loads, whatever you have said, na. So when the machines start at that period of time, the impact short load is the main reasons maybe to failure. But for that, if the material is not so much defective, in that particular cases, this particular shock load may be the less important here. Okay, rather I think fatigue failure is the most important part. Okay.
Yes, sir. Bending fatigue.
Yeah, bending fatigue. Yeah, you can say that.
Yes.
What about the last one, last picture? Can you remember?
Sir, due to thermal expansion contraction, it may happen.
Yeah, thermal expansion. The friction due to frictions. But what are the materials that basically used in order to prepare this particular tool? Do you know?
Sir, tools. Sir.
Tool steel, right? So those are the element that basically those are used for preparing the tool steel. These are highly temperature highly stable things like tungsten carbide. Okay, means tungsten, the element that basically used to prepare the steel have in order to have the high strength and as well as in order to have the high temperature properties like the
high speed steel.
So high speed steel, tool steel, basically these are the few specific steel used for preparing the gear. Okay, so here the temperature effect, those effects are relatively less important as compared to the fatigue and the bending fatigue. Those things.
Sir, it can be pitting.
Yeah, you can partly say. You can partly say. Now, what about the last figure?
Sir, here due to low temperature.
Sir, why HSS steel? Can you explain? Will you explain why HSS steel?
HSS steel?
Means why it is used for these components? Gear, rail line.
No, not rail line. Gear, you can say. Rail line actually paralytic steel used, but gear, high strength steel or HSS high speed steel basically used to ensure that high performance would be there and in order to fabricate that particular things. So basically high HSS steel, it has the excellent mechanical properties like strength, the hardness would be very high and the toughness is relatively high. Okay, so the material should experience high load as well as the high temperature things. So the material which we need to use, so that must have or that must encounter those things, those problems. So that is why the HSS steels are basically used. And in order to develop that, the main role that generally plays to give those excellent properties are the tungsten, the iron-based alloys, and the alloying elements, the expensive alloying elements are used like tungsten, titanium, chromium. Okay, and of course the carbon is there. So this is a part of a metallurgical part. Okay, so if you want to go into details, so then you have to study about the alloy compositions. Okay. the specific heat treatment that the engineers generally follow in order to develop the suitable microstructures. Okay, and actually, if you are able to develop these specific alloys along with the specific heat treatment and followed by the suitable microstructures, then you can achieve those the excellent mechanical properties, and you can ensure the engineers that yes, it is suitable for using in the gear purpose or the load bearing purpose. Okay.
Okay, sir.
So what about the last one?
It is a rivet failure. Means in Titanic, the rivets are pop up due to the ductile to brittle transition.
Yes. Very good.
Yes, sir. Due to the low temperature, the ductile material transformed into
brittle material, and the rivets are pop up, and this happens.
Now, can you tell me that why rivets are popped up or pop up, or is there any other reasons? I think you have seen the Titanic movies, right? So there, I think you have missed some parts. Okay. So not only the ductile to brittle transition is there, but also impact loading also there.
Yes, iceberg.
Iceberg.
Yes,
okay.
Iceberg.
So two things you need to keep in mind here. Okay, three things like rivet joint. Okay, then the impact loading conditions, and the third one is the temperature. Okay, so that is because and because of that the Titanic ship has failed. Okay, and why the pop-up things can happen? What is the main reasons? And actually, the rivet joint here, I think from that particular, I don't know that is hypothetical or time, the periods of times where this kind of failure has happened. But yes, the Liberty Sea failure, I think you may heard about that. That is also happened due to the same failure. Okay. And but there actually the rivet joint was not there, but the joining, the welding of ship, the ship that generally used for that period of time, that was welded ship. Okay, so there also due to having the high loading condition as well as the temperature, the materials may fail. The ship failed, or the ship breaks into two parts. Okay, so here I think from this particular figures you have roughly get some idea about the different types of loading and how the material fails during service life due to having different type of loading as well as the combinations of loading or the individual loading conditions or the factors that actually influence the mechanical performance of a material. Okay, and considering the last one where the microstructures may play an important role or generally play an important role for the mechanical performance of a material. Okay. As you have said, the rivet pop-up, so that generally maybe happens due to the electrochemical reactions of the materials which come into contact with the environment, such as moisture environment or any other adverse environmental conditions, as well as when the impact loadings are acted on that particular ship, so that actually enhance the deteriorations of the rivet joint. Okay. So that may be one sort of reasons for the rivet failure. And when I am talking about the welded joint failure, so there actually people avoid the rivet and replaced with the welded joint in order to rapid production of the ship during Third World War. Second World War, I think. So in that particular case, sorry.
So can you repeat the occasion? Is the Second World War's the weapons regarding that.
আরে যখন ওই তোমার জার্মানি না আই থিঙ্ক ওই সময় যারা প্রচুর লিবার্টি সিপ বানিয়েছিল, হ্যাঁ, সো I think that time period was 1945, I think. In that period of time. So, yeah. So in that period of time, the engineers or they actually enforced to prepare or enforced to fabricate lots of seep, which actually used to, to transport the soldiers from one place to the another place through the sea. Okay, so in that particular cases, they actually avoid the rivet joint because in order to follow the rivet joint process, then the time was taking too much. So that is why the engineers have developed the welding joint. Sorry.
Oh, sorry, sir.
Okay, so there, as they followed the rapid process, so they have encountered several problems like, the joining things. It is one sort of casting process they are following. Okay, so whatever product they have developed before joining, that means the plate or the rods they are using. So that particular parts were processed through the several heat treatment process as well as metalworking process, and by doing the several tests, they have come into the conclusion that yes, that the plates or the rods have a certain specific mechanical properties. But when they went through the joining process, so there again they come they come at the initial positions, like they come with some casting methods, because at the joining points, some materials have to melt, and then the melting pool will join together, and in this way, I think joining happened. So again, that particular microstructure at that particular region was the cast microstructure. Okay, and if you know a little bit well about the difference between cast microstructures and the heat-treated or process microstructures, then I think it will be quite clear to you. Okay, because in general, you just know about that the cast microstructures are a little bit weak as compared to the process microstructure. So that is why at that period of time also several failures happens. Okay, and several ships has drawn into the sea rivers. Okay. So in this way, actually engineers has tried to find out the proper reasons why this failure happened and what we need to do for further improvement of the material performance. So in this way, actually the development happens. Now here in these figures, we may come to another conclusion by seeing the fracture surface of the broken pieces, okay, or the broken material. So can you just tell us that what types of fractures we generally see in the broken surface? Can you categorize the fracture surface based on this fracture morphology? In rough scale, actually, we can see the fracture surface of here as well as the difference between the fracture surface of at this position. These are similar or different?
A different type.
I'm giving another examples, right? If you have the copper wire and if you pull it apart, okay, and in other cases you are using glass, okay, and then you just fell it down to the floor. In these two cases, will the fracture, the appearance or fracture surface would be same or different?
It will be different, sir.
Different.
So what kind of difference you will observe?
So for the tensile failure, we will be observing elongated protrusions.
Don't go the particular specific, the loading conditions. So just just to talk about the fracture surface. Based on the material, you can say the material physical properties or the chemical properties. If I talk about the strength or hardness of the copper as well as the glass, so the strength and hardness would be same for these two cases?
No, sir.
In which cases the strength would be high or the hardness would be high?
So for the glass, the hardness would be high.
For the glass.
So have you seen the broken surface of the glass? So is it the surface is flat or any haziness you can find, or the rough surface you can find?
So,
It is flat.
Yes, sir, it is flat.
It is relatively flat, right? As compared to the broken metal surface. Okay. So in that way, you can categorize the fractures into two types, like brittle fractures and as well as a ductile fractures. So from the factographic point of view, you can say that the brittle fracture surface are relatively flat, as well and the ductile fracture surface consisted of lots of the voids and dimples. Okay, so better to say dimples. So in that way you can categorize. So when we will go into deeper about the fracture surface, then it will be very clear to you. Okay, so as per the course, we can start our class with the very simple mechanical test, which is the tensile test. Okay. After that we will talk about the hardness test, as the hardness test is generally follow a type of compression test. So that is why I will start the hardness test a little bit later, after covering the tensile as well as the compression test. Okay. Now, as I said in the earlier slide, that materials generally failed by different loading conditions, considering the different loading condition, not a single type of loading. Rather, sometimes it fails with the combinations of different types of loading. Now, for simplifications, we can start with a simple type of loading or a single kind of loading, that is, let's say, for tensile loading conditions. Now, the first question that I have put here, that is why testing of material is required, that part is already covered. Now, when we talk about the tensile test, then the two questions we need to keep it, we can ask about that. Why engineers do the tensile test? Okay, apart from the purpose that I have said in the earlier, why we need to go for the tensile test?
Sir, actually by tensile test, we can measure that how strong the material before stretch, it can stretch before it breaks, sir.
Okay. So we need to find out the places or the particular load displacement conditions, like at what load the materials will fail, or at what load the material will start to deform. Okay, something like that, no?
Yes.
So if you if you said just like that, then the basic two purpose will come into the picture. So one purpose is that the design perspective purpose, and another is the manufacturing perspective. Okay, so design perspective is generally considered when the material deforms elastically. Okay, that means you know about the elastic deformation. Do you know about the elastic deformation?
Yes, sir.
Yes, sir.
So what is that?
So deformation that can easily go back to its original position.
Yeah, that means if you release the load, then it will again come back to its original position, right? So when the material generally design, or let's say for the bridge, or the buildings or these things, or I can say that the the engine, okay, the aeroplane engine, the blades, those are basically designed considering the elastic properties, okay, because the engineers will not allow the material to extend or deform plastically or deform in such a way where permanent deformations will retain into that particular material. So engineers will not consider that. Okay, so the design purpose generally considered following the elastic deformation perspective. Okay. Now I said that the manufacturing part. Okay, manufacturing means the fabrications or certain cases, the metalworking, as well as certain cases you can find that we need to cut the material in order to give the complex shape. Okay, so for that particular purpose, for cutting purpose, it is not so important. Rather, the manufacture, the metalworking purpose, where you need to deform permanently. There, the permanent deformation is the important, important parts. Okay, so that is why engineers, the main objectives for doing the tensile test, to know the regions up to which the elastic deformations will happen, and up to which the plastic deformations will happen without fracture. Okay, so is that clear?
Yes, sir.
Yes, sir.
Okay. Now, can you please differentiate between the failure and fracture? What do you mean by failure and what is fracture?
Sir, failure means the material.
Sir,
was
total damage of.
Okay, one by one, please.
Yes, sir. Sir, the material was designed to serve a purpose. If that purpose is not fulfilled, then it fails. But when we are talking about fracture, it actually fractures physically. It actually fractures.
Okay, very good. Any other students? You can add any other points?
Sir, for failure, we mainly consider up to the yield stress point, and for fracture, we consider up to the fracture point.
Sir, I think...
Okay, the failure part you have not said correctly. The previous one you have said, he said quite correctly. Okay.
Fracture is a kind of failure, and failure actually means that the purpose is not served.
Yeah. Very good. So is that clear? The first one we have said and the last one we have said. So these things actually are quite correct. Okay. As compared to the second one, we have said the failure is you can categorize up to the yield strength or yield stress level. Certain cases you can you may write, but not in all cases. Okay. So here. Whenever we will talk about the failure and fractures, you can separate the two things. Okay, in this way, here we generally do the tensile test up to the fracture. Okay, where the permanent elastic deformation part is there, the plastic deformation part is there, and the fracture part is there, where two parts, where the one single piece will separate into two or more pieces. Okay, now by plotting the tensile test results, we can separate the regions. Okay, quite clearly. Now, the question is, how do different material fails under tension? Okay, so here this particular questions you have already answered. Now the next one, that how the tensile test can be carried out. Okay, as I said, now we need to we must have certain objectives, and in order to fulfill that objectives, we need to go for tensile test. Now, a tensile test result can be represented by plotting the results from results of the load versus displacement or the stress versus strain. So we will talk about the definitions of stress strain later on. But in order to get that particular results, how we can do the tensile test, okay, or what are the what are the things we need to keep in mind before doing the test, and what are the comments that we need to say or we need to tell to the operators who is operating the test. So can you please add a few points regarding that? So I think you most of all are the third year or fourth year students, right? So
sir, command means the procedure of the test or something.
Yeah, but specifically, can you say that what are the procedure or what are the main comments that you need to tell to the operator? The basic things is first you need to fabricate the specimen.
Basically,
right?
stress the material from both sides.
Sorry?
By giving a load, static load, we stress the material.
But
So first we create a dumbbell-based shaped specimen.
Yeah, first you need to have a specimen, right? Tensile specimen.
Yes.
Correct.
Sir, actually, we have to mark two ends. I mean, that is the gauge length. So then we need to put that into the two grips of the machine. I mean, the testing machine for in which the tensile test is carried. Then actually, with the gradual increase of the tensile load, we mark the elongation with respect to the corresponding load. And after each increment of the load, we mark this increment, and with the help of that, with gradual time passing, we get that graph. I think that's it.
Any other? Can you add any other points? I think you have said correctly, but you missed a lot more things. Okay.
Sir, also an edge is preferred to hold into the machine.
Any other? First, you have to specify the tensile specimen. Okay. Certain cases, that is most of the cases, you may find that the plates is used, okay, or the long bar is used. So, in order to find out the mechanical properties of long plates or thick plates or thin plates or the long bars, solid cylindrical bars or solid rectangular bars, it is not that you directly use those plate bars to do the to know about the tensile properties of the material. Okay, so you have to fabricate the specimen. Okay, now the question is what sort of specimens you will fabricate. First you need to know, na? So what sort of specimens you need to fabricate? First give me that answer.
A dog bone shaped material.
How do you know?
So because the specimen must be held securely within the jaws of the testing machine. So we need an arrangement for that.
Okay, I agree with that your answer. But the problem is if someone has prepared the dog bone shaped specimen, and for same materials, if someone has prepared the other well-known shaped materials or the specimen, then in two cases, will the results that you will get will be the same? The same materials. You have fabricated the specimen from same materials. Are you getting my question?
Yes, sir. Sir, if you repeat the question, it would be better to understand.
Sorry?
Sir, can you please
Yeah, okay. My question is, ধরো একটা কেসে তুমি ডগ বোন শেপ স্যাম্পল বানালে, আর একটা কেসে হয়তো তুমি একটু ফ্ল্যাট শেপ স্যাম্পল বানালে, ঠিক আছে, সেম মেটেরিয়াল থেকে। সো in these two cases, can you get the same result because you are fabricating the specimen from same sort of specimen, same sort of plates?
Because
when we will increase the load, then the jaw won't be able to hold the flat edged.
না, তুমি ধরে নাও যে জ ধরে নিচ্ছে, হ্যাঁ, জ মানে স্পেসিমেনটাকে হোল্ড করে রাখতে পারছে।
প্যারামিটার স্ট্রেস মেজার করে তাহলে তো সেমই আসবে, লোড মেজার করে আলাদা আসবে, মানে লোড।
ওকে, সো
স্ট্রেস কনসেন্ট্রেশন কি এখানে কোনো ফ্যাক্টর প্লে করবে?
না, my question actually, I am just asking this sort of question because whenever we fabricate certain specimen, we need to follow certain standards such that your result will be representative to the engineers community or to the research community. Okay, people will verify your results.
The tolerance grids are that you are saying.
Sorry.
These industrial standards.
Industrial
tolerance
standard.
grids.
Industrial standard or the ASTM standard, okay, or Indian standard that you need to follow to fabricate the specimen. And of course, based on your machine capability, you need to follow a certain specific standard. Okay, like if you have the very thin flat specimen, thin flat samples or thin flat plate. Okay, so in that particular cases, you may not be able to fabricate the solid cylindrical specimen. You need to follow a certain standard where the flat specimen can be mentioned. Okay, so in that particular cases, you must have to follow a certain standard, whether it is ISO standard or British standard or ASTM standard. So I will send you the ASTM standard for tensile test. There you will find the different types of tensile specimen that you can fabricate based on the sample availability, based on the machines that you have, means the capability of the machines that you have. Okay, you can fabricate, and if you follow these standards, then whatever the shapes you are following, you may get a quite comparable result. Okay, but in another cases, if you don't follow the standards, then in that particular cases, of course, your load will vary, but due to having the constraint effect, your stress may also vary. Okay, so for same materials, if you fabricate the two different specimen geometry, but you are not following the standards, then you may find that the stress that you are reporting for a particular material, that stress may vary. ঠিক আছে, তো সেই জন্য আমাদেরকে স্ট্যান্ডার্ড ফলো করে স্পেসিমেন ফ্যাব্রিকেট করতে হবে। না, অফকোর্স হ্যাঁ বলো।
Sir, why is it so? Because elasticity or the other moduluses of elasticity are generally material property. So even if we change the cross section, it should remain the same, the values.
Yeah, the elasticity property is a material property, no doubt about that. The problem is when you report, we generally try to find out the strength and elongation part, right? So when you do the test to find out the strength of a material, so the strength results you may get the quite wrong results you may get. Okay, if you don't follow a particular standard. Okay, that I said that the sample constraint effect. Okay, যদি ধরো খুব ছোট স্যাম্পল বানাও without maintaining the length to cross sections ratio, and another cases you have prepared the very long specimen, length to cross section ratio is different. So in that particular cases, you may not get the same result. Okay, even though you have generalized your data by dividing the load with the cross-sectional area. ঠিক আছে? সেই জন্য আমাদের একটা সার্টেন স্ট্যান্ডার্ড ফলো করতে হবে, যেখানে দেখবে মেনশন করে দেবে what should be the length to cross-sections area, cross-sectional area, that is L by A ratio or L by root A ratio. ঠিক আছে? তোমাদের আমি স্ট্যান্ডার্ডটা পাঠিয়ে দেবো, একটু ফলো করে নিও, একটু দেখে নিও।
স্যার এটা কি স্যার মানে
এটা হচ্ছে ক্রস সেকশনস অফ দ্য স্পেসিমেন। ওকে
ওকে
ক্রস সেকশন যদি তুমি সলিড সিলিন্ডার যদি তুমি প্রিপেয়ার করো, আই উইল শো ইউ ইন দ্য নেক্সট স্লাইড অলসো। ঠিক আছে? সো ফার্স্ট থিংস ইউ নিড টু ফলো the certain standard to fabricate the specimen, and of course before that you need to keep in mind the machines that you are using, so it's the machine's capability or the load bearing capacity. Okay, now the second thing is you have to tell the operators what is the specimen geometry that you are following, so the length of certain regions you need to tell the operator. Okay, now the next thing is what should be the loading rate. Means you are elongating the specimen, you are stretching the specimen, so what should be this stretching rate? So you need to tell to the operator. If you do the constant displacement, the types of methodology, so then you need to tell the operator what should be the loading rate or the velocity, cross-head velocity, which we generally say. ওকে, এই দুটো না বললে কিন্তু অপারেটর কিন্তু স্টার্ট করতে পারবে না। না হলে ধরো তুমি লোডিং রেট বললে না, হয়তো অপারেটর স্টার্ট করে দিল একটা আরবিটারি লোডিং রেটে স্টার্ট করে দিল, মানে হয়তো খুব স্পিডে মেটেরিয়ালটা ডিফর্ম করে যাবে এবং দেন ফেল উইল ইউ ক্যান গেট the results. Okay, because if your operator is in a little bit hurry, so he may increase the loading rate, so you may get one sort of results. And in other cases, when your operator is a little bit lazy, so in that cases he may start relatively in slower rate. Okay, so in these two cases, for the same material, for same specimen geometry, whatever you have followed, you may get the different results also. Okay, so that particular part is you can call it as the effect of straining rate on mechanical properties, or the strength elongation property. Okay, it are একটা example that I can tell you, that if you do the tensile test and parallelly if you do the impact test, okay, so can you differentiate these two tests based on the straining rate, in which cases the straining rate is very fast and which cases is relatively slow?
So impact test, it should be much faster.
Much faster. So that is why, though the impact test, the loading conditions is little bit different, but if you go in micron scale or in micro level, then you will find that at the crack tip, okay, means where the crack generally start to propagate, initiate and then propagate at that particular regions, you may find that the material is experiencing the tensile kind of force. Okay, and that is why the cracks are, the crack opening generally happens, and then crack will propagate from one end to the another, and the materials fractured into two pieces. Okay, so that is why the straining rate is another important part. Okay, and of course the third one you cannot avoid, that is the temperature. Okay, but most of the cases we do the tensile test at room temperature. So in that cases roughly you may forget about the temperature. Okay, but in order to do the test at very low temperatures, you may find the different sort of results. Okay, for the same material. Now, how the tensile test? Okay, you have done the tensile test, or you have completed the tensile test, and now the time is to take the results. Okay, so you have got the results like with respect to time, you got the result time, then load, and then displacement, right? So how you can plot the data that you have got, how you will represent your data such that you will get a lot more information for that particular material. So though I have said it several times, so can you please repeat these things, how you can represent your data? Earlier I have said the stress strain data, right? Stress strain curve. So, but initially you generally get the load versus displacement data.
Deflection curve, yes.
Okay, so load displacement curve we can represent. But my question is, can we always represent the load versus displacement curve, or we need to refine the data such that we can represent the data in more convenient way, like stress strain curve? Why not load versus displacement data we generally not represent?
So stress strain is a material property, like the stress strain curve is a material property, whereas load displacement.
No, stress strain curve the material property we have bolo na. So before commenting any particular things, you
stress strain curve to ওই মানে এক্সপেরিমেন্টটা হচ্ছে যেটা সেটা
load displacement curve টা ওই এক্সপেরিমেন্টারি ডেটা। তাহলে আমরা লোড সবসময় লোড ডিসপ্লেসমেন্ট কার্ভটা না প্লট করে why we generally follow the stress strain curve? আমরা জেনারেলি স্ট্রেস স্ট্রেন কার্ভই দেখি না মোস্ট অফ দ্য কেসে।
Sir, to navigate the effect of dimensions, sir.
Sorry. I think you have said a little quite correctly. What you have said, please repeat.
Sir, to navigate the effect of dimension.
Yeah, to navigate the effect of dimension. Though you have followed the standard, ASTM standard, but when you fabricate the specimen, sometimes the manual error can retain there. Okay, let's say you have fabricated a cylindrical specimen and the gauge length is, let's say, for 25 mm in one sample, and the diameter is, let's say, for 5 mm. Okay, and another cases the gauge length is 26 mm. And the gauge diameter is a little bit different as compared to the previous one. Okay, so in order to encounter that particular problem, you have to represent the data such that the quite equivalent results you will get. If you plot the load versus displacement data, so you will find that for greater cross section material, you will find that the load requirement is relatively high. Okay, so then in that particular cases for same material, you may get the different results and you will confused with your data. So I think you have understood that particular things, right? Hello.
Yes, sir.
Yes.
Okay, so the basic part is to represent that data, you have to first collect the data, which is the load versus displacement data. Then in order to generalize, whenever you do the test, it is not that you just do one test. You have to do the several tests and then you have to take the average data and then you have to represent it. Okay, such that the data that you are getting at the first cases, that data is correct. Okay. Certain cases you will find that if your material contained a lot more defects, then your first data may not be the accurate data. Okay, then that is why you need to go for the serial test, and you have to be so sure that your data, whatever you are getting, that is quite correct. Okay, now the defect that I have said that the material can retain, that material can contain a lot more defects. So that is a different sector or different part which actually emphasize the fracture micromechanism or fracture mechanics part. Okay, so that particular part I will not cover here. That is a long, vast part. So if you have a certain interest, then you can follow the book of Harjbag. Okay, if someone wants to know about that, so you can follow the fracture mechanics books, elementary fracture mechanics book written by Harjbag. Okay, so that is a separate issue you can follow. Now here after getting the data, how you can use this tensile test result, how you will use, or what will be your basic aim after doing the test. What engineers do after getting or after doing the tensile, after doing the tensile test, or specifically I should say.
So we plot the stress strain curve, and from there we
you plot the curve and you get the informations. Then how you will use it?
Sir, means find the dimensions of the cross. Find the dimensions of the cross section.
Sir, for that material, we get the ultimate stress or the yield strength.
Determine the factor of safety
design.
Yeah, to determine the factor of safety, yes, one aspect that we can cover, okay, or one aspect is fulfilled. Okay, another thing is that when we develop the material, first of all, based on the mechanical properties point of view, the factor of safety that we can set. The second one is if we want to develop the material further such that the same material will give the more or the better mechanical performance, then we can go back to the heat treatment schedule. Then we can develop the microstructure, that means which are the most influencing factor which control the mechanical performance. So we can alter those factors by changing the heat treatment schedule, or even if we go back to the initial positions, then we can also design the material considering the compositions of the material. Okay, so in that way we can develop the material. Now, if we see the fracture surface of the material, okay, or you have done the tensile test and you got the fractured specimen, and if you investigate the fracture surface, so there also you will get some information like whether the material failed in brittle fashions or whether the material fell in ductile fashions, or it is a combination of ductile plus brittle. If we, it generally knows, in general cases, we generally know that if the material fails in ductile fashions, so that means that the material will give more elongation as compared to the strength. Okay. But if the material fails quite ductile, brittle fashions, then we can roughly say that the material is experiencing or sustained, containing, having a more amount of load, or the material can hold a more amount of load. Okay. So roughly we can say that because the strength and ductility both are inversely proportional. Okay, in general sense. In general sense, both are inversely proportional. If a material is having high strength, then the material may fail with a little bit, very low strain level, at very low strain level. Okay. But if a material, showing with a lot more ductility, then the material strength or the material can hold a very low amount of load. Okay. So for real examples, I can tell you that if you do a tensile test for aluminium samples and if you do the tensile test for high strength steel, in these two cases, you will find that the steel will show you high strength, but aluminum will show you the high elongation, where the strength is relatively low as compared to the steel one. Okay, so these are the things that we can know about these things. If you compare the same material, then you can adjust the parameter, influencing parameter, such that you will get the high strength level as well as the quite acceptable ductility level. Okay, that means you are by seeing the fracture surface also, you have tried to understand that yes, we need to get the fully ductile fracture surface, or quite intermediate kind of fracture surface where both ductile fracture regions as well as the pre-fracture regions could be there. Okay, such that we can control the strength, the balance of strength as well as the ductility. So I will represent those things graphically in the subsequent classes or subsequent slides also. Okay, the last things, that is, what are the factors that influence the tensile property that I already told you? These are the strain rate, the temperature, okay, and the specimen dimension that I am not talking about these things here. Okay, but the main two important factor is the temperature as well as the strain rate. Right? If I forgot some things, or if I forgot any important points. Now coming to
also the microscopical defects affect the
the microscopical defects, or I would say the microstructural parameters. Very good. I think someone has added this particular part. So microscopical defect is an important part, but we always consider that whatever material you have developed, that particular material is quite homogeneous, as well as this particular material will not contain any microstructural defect. Okay, can you tell me that I don't know whether you don't know or whether you know or you don't know these things or not. That is what sort of defects that material in a material that particular defects can retain. Type of defects. Do you know the type of defects?
Yes, sir. We started in facts like the point defect and surface defects, like that.
Okay, very good.
So line defect.
Line defect. What is the name? Specific name actually. Line defects has specific name. Dislocation. Have you heard about the dislocation?
Screw dislocation.
Screw dislocation.
So in 2D, the line defect is there. Or even in 3D, we can say that the planar defect, right? So if you assume that...
2D, can you repeat, sir, the name?
At 2D, you can say it as the line defect, or even in 3D, the line defect will also be there. Okay, so this line defect as well as the planar defect is basically known as the dislocation. Have you heard about the dislocation?
Edge dislocation and screw dislocation.
Screw dislocation.
Screw dislocation.
Edge dislocation. So these are the defects will generally there. So these are basically the microscopic defects. Okay. So you have heard about the macroscopic defects. So have you heard about the macroscopic defects?
In the surface notch will be
but you have said, I think, the things, the surface defects and the surface notch is there. If I talk about the interior part of a material, so there are also certain cases we generally find different macroscopic defects.
So cracks in inclusions, pores.
Yeah, cracks, inclusions. Any other?
Pores,
voids.
Void.
So these things are the macroscopic defect. Okay, so the effect of those macroscopic defect on the mechanical test or the mechanical properties, it is also an important part of studying these things. Okay, though the most of the cases this part will generally covers in the fracture mechanics. Okay, so I will try to cover these things a little bit. Okay, but if time permits, I may go into deeper these things. Acha, can you please give an examples where the surface defects actually hampered the property, the mechanical properties of a material? Where
Sir,
actually
endurance limit.
endurance limit.
So যখন endurance limit হবে তখন surface factor একটা surface finish factor একটা থাকে we include in the corrected endurance limit.
Very good, very good. Places where this, I think one of you have said that the surface notch. If the surface notch is quite large and quite significant, and if it is visible, then it will affect on the tensile properties also. Okay. That means you are actually intentionally you are localizing the deformation region, right? We generally restrict the deformation region throughout the gauge portions, right? But if you are intentionally creating some region or local regions where you want the deformation to restrict at that particular region, then also you will not get the strength versus elongation graph as per the materials that you have studied in earlier where no notches was there. Okay, so that is the things you need to keep in mind. Okay, now come to the experiment part. Okay, here in order to do the experiment, I have said that you need to follow certain standards. So here I have put the ASTM E8 standard. Okay, I generally follow in our the research purpose in ASTM standard, where the standard test method of tensile testing of materials is given. Okay, and from there I picked up the few samples. Okay, 3 sets of samples considering the plate as well as the bulk material from where we can fabricate the round or cylindrical specimen. Okay, now here if you follow very carefully, then you can see that this particular specimen have the different important zone, like the gauge zone, gauge portion is there, and the grip zone, some riveted, some fillet radius we need to maintain. Okay, now can you please tell me that why we need to fabricate the specimen in this particular way, where a specific gauge zone is there, should be there? Why we need to go for that? I have said already. Okay, I have given the answer of this particular questions already.
So to maintain a proper the length to cross-sectional, as you said.
No, actually we are restricting the deformation. We try to restrict the deformation throughout the gauge length. Okay, but that is the reduced cross sections. If we don't reduce the cross section, means if we maintain the diameter from one end to the another end same, so there I think it will be very difficult to identify the deformed region. Okay, because when you do the test, we don't know that from where the material will break. Correct. So that is why we try to intentionally specify the region. Yes, the material would be fail anywhere of this particular gauge portions, not at the grip portions. Okay, not this grip portion, because if the material is homogeneous, it will be very difficult to to break the specimen. Okay, because and also if the material is quite homogeneous during gripping, at the interface of the grip or at the junction point of grip and ungrip portions, there you may find that certain such notch has created. Okay, and as you have said that if the specimen surface contained a visible notch, so from there also the material will fail. Okay, so that is why in order to avoid that particular problem, we have to create a certain regions, the reduced cross sections, where the load requirement to deform the material is relatively less as compared to the other part like grip part. Okay, and the material will fail anywhere of this particular gauge portion. Okay, so that is why we need to do this grip zone. And otherwise, I think for civil engineer cases, we will find that whenever you do the tensile test of a rod, means TMT rebar, so in that particular cases, they try to gauge or they try to mark throughout the throughout the length of this particular rod. Okay, they try to mark. Okay, and then after before doing the test, they take the measurement of the length of the rod, and then after the test, they take the measurement of the whole rod. Okay, not a or the regions nearby regions of the fracture surface. Okay, so in this way, people try to get the tensile test result. Okay, but always you need to keep in mind that if your sample fractured in between the gauge portions, then that particular results you can assume that the result is means quite correct, or you can say that the results is near about 99% correct. Okay, 95 to 99% correct, as compared to the test of TMT rebar. Okay, where the civil engineers people generally do. So here, so that is the things you need to keep in mind: the importance of gauge portions, gauge zone, okay, gauge length, as well as the ratio of the gauge length versus the gauge cross-sectional area. Okay, in ASTM standard, we generally follow the ratio is relative from 4.5 to 5. Okay, so these things you need to keep in mind. Now, the fillet radius is also important. As I said, that if you maintain the homogeneous radius, then during gripping, okay, some dent will create, and some notch portions will create. So that may lead to the failure of the material. So in order to avoid that, you need to maintain the fillet radius. Okay. And of course, people generally follow the fillet radius as per the standard. If your fillet radius is too small, so in that particular cases, you will find that that particular fillet zones will also act as the notch sensitive region. Okay, and the material may fail at the fillet zone also. Okay, so in order to avoid that, you need to maintain certain standard fillet radius. Now, you can say that you generally see that this is the flat specimen, okay, and you have fabricated the specimen from the flat plate, okay. Now, if you don't have the significant thickened flat specimen, you can reduce the thickness of the specimen, but here you need to maintain those ratio. As well as if you have the scarcity of the specimen, you can shorten the specimen thickness, but there also you need to maintain that particular ratio. So here 3 types of specimen you will find, having like the total length of 2 inch and the gauge actually you can separate it considering the gauge length. Like one cases you will find that the length of the gauge is 8 inch to 2 inch to 1 inch. Okay, so you can manipulate these things based on the specimen that you have. Now, apart from the flat specimen, you can prepare the round specimen, solid cylinder. Okay, and if your machines need to fabricate, if your machines requirement is such that you need to fabricate the grip portions by fabricating this sort of things, so then you have to follow this particular, you need to prepare this particular specimens where this sort of things or dent mark is there. Now this is the machines that we generally use in our department to do the tensile test. And here you can see that your machines can be operated electrically or any other the energy generating systems you can use. Okay, and hydraulic pressures actually control the load requirement. Okay, and and here you can see that there are the 2 heads are available. Okay, and the two grip portions are there. Okay, this is the two grip portions, and these two grip portions actually decides, or the holder decides that which sample is suitable for the test. Okay, and as I said that there are two heads are there, so depending on the types of machines, you will find that certain cases the upper head is movable but the lower head is fixed. Certain cases the reverse things can happen. In certain cases you will find that the both heads are moving in opposite directions. Okay. Now before doing the test, you have to maintain the gap between these two heads very carefully, and you have to set the value 0 at the initial position where the load is 0 and the displacement should be 0. And after fixing the specimen, and when you start the test, the displacement will generally happen if you give the rate of displacement is fixed. Okay, let's say for 0.5 mm per minute or 1 mm per minute. Okay, something like that. Now you can maintain this load the velocity or the cross-head velocity, or you can calculate the strain rate. Generally, we use the term strain rate, so you have to divide it. You have to divide first you have to know what is the strain rate, that is the strain divided by time. So you can calculate the strain rate from the data of the cross-head velocity. Okay, so you please try at home that how we can derive the strain rate from the cross-head velocity based on the equation. Okay, now here one things extra things you can use, that is the strain gauge. So you generally find the strain gauge is looking like this. So what is the purpose of using this strain gauge is to measure the displacement very accurately. Okay, this strain gauge is very expensive, so the purpose of using strain gauge is to measure the displacement of strain quite accurately. Okay, but the limitation is it can measure the strain up to a limit. Okay, because the displacement, the gauge displacement is restricted up to a limit. Okay, beyond that you have to remove this particular strain gauge. Okay, and the purpose also to measure the elastic modulus of the material quite accurately. So these are the few things you need to keep in mind. Now in the next class, you please tell me that how we can record the data. Okay, how we can record the data, because we are not putting the load like 1 kilo load or 2 kilo load or 100 kilo load. Okay, just like আমাদের যে দাঁড়িপাল্লা যেগুলো আছে না, ওইভাবে আমরা লোড ইউজ করি না, rather here we are controlling the loads of maintaining the electromotive force, EMF force. Okay, so how we generally record the data and then we represent the data, you please elaborate a little bit in the next class. Now in order to know the tensile test more elaborately, so first we need to know certain definitions like the load. So the load is very simple one, you already know about that. Displacement, it is also known to you. Now if you have the load versus displacement data, so to generalize this data, we need to derive it in terms of stress and strain. Okay, so what is stress and what is strain? I think you have said, but mathematically we need to represent the stress versus strain. Then the elastic modulus, okay, so which is the material property, that is the E. Then the resilience, what is resilience? Okay, what are the information that actually we generally get from the tensile stress curve. Now the toughness, okay, so toughness we will try to understand. The elastic deformation region, plastic deformations region, the proportional limit, okay, elastic limit, the yield strength of a material, ultimate tensile strength, fracture strength, okay, the elastic strain, ultimate tensile strain, the fracture strain. So all these things we will try to understand. Now here in this particular figure, okay, so okay, first come into the definitions of the stress and strain, and then we will talk about the details about the stress strain curve. Okay, so now whatever data we generally get from the tensile test, so we can separate it or we can represent it in two ways. Okay, as you said that the stress you can define that is the load divided by area. So either you can follow this particular formula throughout the test, like from stress the load level 0 to the maximum load level. Okay, that means till the fracture. And similarly you can measure the strain considering the length of the material from the strain at 0 to the maximum strain level. So if you follow this particular pattern, so then whatever the graph you will get, that particular stress strain graph, you can say it as the engineering stress strain curve. Okay. Now, if you follow the patterns where you are evaluating the stress in each sections of time or each time frame, okay, that means when you are keeping the load, you are expecting that your material will stretch, and when your material will stretch, the cross sections of the material will gradually reduce. So if you are able to find out the reduced cross sections, that means during the reductions generally happen due to the stretching of the specimen. So if you are able to measure that particular reduced cross sections each time frame, then you are able to find out the true stress level of the true stress of the material. Okay, from stress is equal to 0 to the fracture stress. Okay, and then you can represent the data. Okay. Now, and similarly, you can follow the same formula for evaluate the strain also. Okay, and then you can represent the true stress versus true strain data. Okay, and you can represent the true stress true strain curve. Now, when you separate the engineering stress strain with true stress strain, so there are, of course, you need to follow certain, the symbols. So there you generally find out the representations of engineering stress and strain like S and E. Okay, here we have used at sigma E, that is engineering stress. Okay, which is equals to the load, instantaneous load divided by the initial cross-sectional area, that is the gauge area. Okay, and the strain, engineering strain, that is E, that is instantaneous displacement or instantaneous length, gauge length, minus the initial gauge length divided by the initial gauge length. Okay, so the symbol we generally follow for engineering stress, either sigma E or S, something like that. In case of true stress and strain, we only use the sigma, and for strain we generally use the epsilon. Okay, so these things you need to keep in mind to separate the engineering and the true stress strain. Okay, so I will come at this particular slide a little bit later, but before that you please tell me that what type of stress strain curve it is here we present in this particular slide.
Sir, engineering
stress strain curve.
Okay. Now, quite explicitly, I have separated the different zone of this particular stress strain curve. So one is the elastic region, right? Now, what kinds of formula that particular regions follow? What sort of formula?
Sir, the Hooke's law is followed here in the elastic region.
Hooke's law is followed here, right?
Proportional.
Yeah, that means the stress is proportional with strain.
Stress is proportional to strain. Yes.
Strain. Okay, so how up to what extent that particular curve is followed, or that particular law is followed?
Sir, up to the proportional limit, sir.
Proportional limit.
Yeah, up to the proportional limit.
That's
now beyond that means if we release the load at this proportional limit position, so the material will come back to its initial position. That means the total length or the gauge length would be 0, right? If we release the load.
Yes, sir.
Now what will happen beyond the proportional limit? Though I have marked the elastic regions up to this position, right? So here if we see that up to these positions the proportional limit is followed, the Hooke's law is followed. So beyond that, what will happen inside the material? Means if we increase the load to some extent and reach at this particular position, then if we release the load, will it come back to its initial positions or not?
Yes, sir. It will come back to its initial position, but not proportionally, or
but not
linearly.
proportionally.
Yes, sir.
Not linearly. That means Hooke's law is applicable up to this position, okay, up to the proportional limit. Beyond that, we have to analyze these things in a different way, right?
Yes, sir.
Okay. I think you have class from 11 onwards. 12 onwards, right? Another class?
Sir.
Yes, sir.
Yes, sir.
Class
Okay, so today,
12 classes.
yeah. So today I will cover a little bit things about this particular graph. Then I will let you go. Huh? Okay. So up to the elastic limit. So I have pointed with this point. I have given the name of this particular point is the elastic limit. That means if you release the load at elastic limit, it will come back to its initial positions also, but not following the proportional, the Hooke's law. Okay. Now, certain cases we will find that the strain at elastic limit is very, very negligible. Okay. And it is in certain cases you may not recognize this particular elastic limit, or you cannot you cannot see this particular elastic limit, or you cannot identify the elastic limit. So in that particular cases, you need to do, or you need to find out, you need to mark a particular point from where you can say that the material start to deform plastically. Okay, that means the permanent deformations will happen beyond a particular point. Okay.
Stress.
So that particular stress you can define as the yield stress. But here I have pointed out here at this particular positions. Okay. So basically, whenever you define the yield stress, so that basically you can define it as the visible stress level, the stress level where the detectable amount of strain the material can experience. Okay, detectable amount of strain. Now, when we compare the stress strain curve for different material, in this particular graph, it is quite visible that from where the material start to deform plastically, right? But in certain cases, it will be very difficult to differentiate the positions, right? So, can you see this particular graph?
Yes, sir.
Yes. So here, can you material start to deform? Sorry, plastically.
Yes, sir. It's difficult to locate. That's why we use the concept of the
proof stress, right?
Proof stress. Yes, sir. Proof stress.
Yeah, proof stress. So considering that particular point, the definitions of the yield stress as well as the proof stress come, right? In certain cases where the detectable amount of strain is is there. So in that particular cases, we directly use the yield stress, and the certain cases where this detectable amount of stress is very difficult to identify. So in that particular cases, we can follow, or we can follow the definitions of proof stress, where how we can actually how we can identify the proof stress. Can you please explain those who has given that particular definition, or who have said about the proof stress? I think in this particular graph it has already said.
Yes, sir. At the 0.2% strain.
Means you have to take the offset of 0.
Yes, sir. Offset.
Okay. So offset with respect to what? Means if you know the proportional limit quite well, then you have to take a you have to take a straight line, okay, which is superimposed with this particular graph, and then a curve. But then you have to take the offset of from 0 to 0.2%. Okay, certain cases you will find that they have taken 0.1%. Certain cases you will find that they have taken 0.5%. Okay, so don't confuse with this particular results. Okay, that depends on material to material. Okay, so if you release the load, now the question is, if you release the load at 0.2%, the proof stress, okay, then will it come to its original positions or not?
No, sir.
Sir, no. Then the 0.2% already deformed plastically.
Yes, so 0.2% strengths will retain there. Okay, so these things you need to keep in mind. Now, beyond the elastic limit, or beyond the elastic limit, you have said the plastic deformation will start. Okay, that means the material will start to deform plastically, or the permanent deformations will start. Now, if I release now in this particular graph, if I release the load from this particular positions, okay, now what would be the material strength? What would be the material strength that will retain?
So you have to draw a line parallel to the elastic.
Yeah, parallel to the elastic, elastic line, right? Yes. So then we have to correctly measure the permanent deformations, or the true deformation, or the true strain of the particular material, or the strain, rather strain. If I draw the engineering stress strain curve, then the engineering strain. If I draw the true stress strain curve, then the true strain. Okay. Now here you can see that this permanent deformations means up to the ultimate, the tensile ultimate stress level. So you can see that we have separated into two regions, like another is the strain hardening region. So here you can say that the yielding region, that means the no increasing in stress is happening. Okay, but though the permanent deformation is going on, so you will find the definition is the yield point phenomena. In certain cases, you will find this definition, that is the yield point phenomena, where no increment in stress is happening. Okay. Now beyond that, the increment in stress is generally happened, and that is because of the strain hardening. That means the material is resisting to deform for the deformations. So that is why the strain hardening we are saying. That means the resistance that actually material gives to deform that particular material. Now, can you please tell me what actually happens at UTS point, the ultimate tensile stress point?
Necking starts, sir. Necking
starts. So beyond that UTS, what kind of deformation is happening? Means is the deformation deformations happens throughout the gauge portions, or some specific regions the deformation is going on?
In the neck portion, the deformation continues.
Okay, that means that when the necking start, then the localized deformation is going on. Okay. Now, can you please explain that beyond the ultimate tensile stress, why the curve is dropping in the fracture, or the stress level is dropping?
Yes, sir, because the area of cross-section area is decreasing.
So actually, the material strength is decreasing now.
Yeah, but why? When it's, as per the engineering stress strain curve, you have said correctly. But if you follow the true stress strain curve, you are wrong.
Yes, sir, I can explain, sir. In the engineering stress strain curve, actually the stress is calculated based on original area, but after the necking occurs, the cross section area is decreasing at the necking portion. That's why we generally get lesser load compared to previous portion, but cross section area remains the original area. That's why, sir.
Yes, very good, very good. So you all please follow his answer that the load requirement will reduce based on the localized deformations. Locally, when the necking start, the deformations rate will be relatively fast at the neck region. Okay. So that is why the load requirement will reduce as well as the curve will go down to the till the fractures. Okay. Now, if we plot the true stress strain curve, then what will happen till the fractures? Will it follow the same kind of pattern, or will it follow the different pattern?
To follow different patterns, sir.
So what will happen from yielding to the fracture?
So the curve will go above.
But that will monotonically it will increase. Okay. Now at the U-test you have said one of you have said that at the UTS level the cross-sectional, the localized deformation will happen and the load requirement will be reduced. But why in case of true stress strain curve the curve will gradually go up?
So because I think it is based on the instantaneous cross-sectional area.
Yes, based on the instantaneous cross-sectional area. Though the load requirement will reduce, but the rate of decrement of cross-sectional area will be high, relatively high. Okay, so that is why the overall result will lead to the increment of the stress. Okay, so that is the difference between this engineering stress strain and the true stress strain curve. So I think today this is enough. In the next class, I think Monday, we will talk about the definitions of each part. Okay, and
Sir,
try to understand these things. হ্যাঁ বলো।
স্যার পিপিটিটা পাঠিয়ে দেবেন একটু আমাদেরকে।
পিপিটিটা এটা কমপ্লিট করার পরে পাঠাবো, হ্যাঁ তোমরা একটু নিজেরা পড়ো, আমি এটা কমপ্লিট করে দেওয়ার পরে তারপরে পাঠাবো, হ্যাঁ।
ওকে স্যার।
ওকে স্যার, থ্যাংক ইউ স্যার।
Thank you, sir.
Thank you, sir.
Are you enjoying, na?
Yes, sir. Yes.
Yes.
If you have any questions, please ask me. I will try to give the answer. Huh? ठीक है, चलो आज के, हाँ?
Sir, we can leave now.
Yeah, you can leave.
Okay, sir. Thank you, sir.
Thank you, sir.
Welcome.